Welcome back to West Virginia. Here we are in our great state. So, I'm ready for joke of the day because it just makes me so happy. It's the best part of the day. Are you ready? Let's do this. So, although the invention of the shovel was groundbreaking and the invention of the broom truly swept the nation, it was the invention of the wheel that really got things rolling. Okay, let's roll ourselves then into piecewise functions. Piecewise functions, basically, when you create their graph, you graph it in pieces. That's why it's called piecewise function. You take each piece of the function, because it is in pieces, and you graph the first piece up until a certain point. You graph the next piece up until its particular point, and then you graph the next piece up until its particular point. So you're graphing it in sections or in pieces. So let's take a look. The best way to get into piecewise functions is to just simply do a bunch of examples. So I've got 4 examples they're going to be looking at. The first example is like a real world situation so that you can see, where would I even use this stuff? Now granted, this is a little bit of an old example because we're talking about a cellular phone plan. And now everything's unlimited minutes. So this doesn't really apply, but it's a great example so you can see how this comes about. So in this particular cellular phone billing plan, what's going to happen is it says we're going to be paid, we are going to pay $60 per month, and that buys us 450 minutes. Now that is a flat rate. Giving that company $60, we will have 450 minutes worth of phone talk time. And so then anything beyond that 450 minutes, once we hit our 450 minute cutoff, they're going to charge us 35 cents for each minute beyond that. So you can see that the plan is being charged in pieces. So let's take a look at the pieces. So I'm going to look at the cost of this. So it's a cost function. And what I'm going to do is I'm going to say, let's let that X be the number of minutes that I want to talk. Number of minutes of talk time. And I want to say, okay, based on that number of minutes, what will my cost be? Now recall that for the first 450 minutes, it is a flat rate of $60. That's all there is to it. So that means that $60 will be my cost for the first 450 minutes. So that will go from 0 minutes up to 450 minutes. Now notice, and this is getting all crowded out, let me fix that a little bit. Let X equal, there we go. Now notice the way I wrote this, because I put a less than or equal to sign on this one, saying that the 0 is smaller than X, so the X is going to be bigger than 0, but it's also okay for it to be 0. I mean, really, we don't want to have the cellular plan and not talk at all, but it is okay to talk 0 minutes. We're still going to get charged $60 just for having the plan. But this will go up to 450 minutes, so anything bigger than 0, smaller than 450. Now, is it okay to talk for 450 minutes? Actually, it is okay to talk for 450 minutes. So I messed up here, and I do need to put an equal to part there on the 450. Now remember, anything beyond 450, I'm going to get charged extra. So the second criteria here is going to say, okay, anything where that X is greater than 450. Now notice I'm not putting an equal to part on there. I'm going to clean that up. It looks like a 7 right now. I'm not going to put an equal to part on this because equal to would indicate 450 itself. And it's not going to be 450 itself, because if it's 450 itself, that goes back to this part, $60. This is anything beyond the 450. So I do not want to put that equal to part on there. Number of minutes. And I'll just leave it at number of minutes. Okay. So now recall, in order to figure out how much are we going to be charged once we go over that tipping point, beyond that 450, what are we going to be charged? Now recall, we will still be charged our $60 flat rate. That's not going to change. So I'm going to take my $60 and I'm going to add to that a dollar amount. Now what I'm going to add to that is 35 cents for every minute beyond. Now what a lot of people do, let me get this out of here, I'll bring it back in, and it's just going to take too much space. Now what a lot of people do is they say, okay, that's going to be 35 cents times each and every minute. But now think about what this is indicating. This is for all of my X's that are greater than 450. So let's pick a good easy number to work with. Let's talk about 500 minutes. So what that would indicate is I'm saying my x is going to be 500. Now if I make my x 500, I'm going to take 35 cents times all 500 minutes. Is that how this works? No, not at all. I'm only being charged 35 cents for all the minutes beyond 450. Not all 500 minutes, just those 50 minutes beyond 450. Just those 50 minutes. So how did I get those 50 minutes? Exactly. I took the number of minutes, which is x, and subtracted 450 from that. That will tell me how much I've gone over. So instead of 35 cents times x, it's going to be 35 cents times x minus 450. Again, let's think this through. Let's say the x is 500. Then what that's going to indicate is I'm going to take my 500 and subtract 450. That tells me 50 minutes over my allotted 450. 50 minutes over. Those 50 minutes are what are going to get multiplied to my 35 cents. That charge is what's going to be added to the $60. And that will give me whatever my cost is going to be in this type of situation where the x is greater than 450. So here is my cost function. Anything from 0 to 450, including 450, will be $60 flat rate. Anything beyond 450, I will take this cost function, subtract 450 from those minutes, multiply it by 35 cents, and add 60 to it. So now what I'm going to do is I'm going to graph this particular cost function so that I can get a visual of what it will look like. Now normally when we graph, we would do a 2D coordinate plane that looks like this. My x-axis here, recall, that represents minutes. Now I'm not going to utilize all four quadrants, and why would I not do that? Exactly right. This represents minutes. I can't have negative minutes, so I'm not going to have this end of my graph. Now this is going to be my cost function. Remember, C of x typically represents a y. It's just a different way of writing y. It still represents y, but it's saying, oh, this one's a function, it's special. But this is still representing y. Once again, I'm not going to use part of that axis, and how come? Exactly. This is cost. It is dollars. It makes no sense down here to pay negative dollars. So I'm really going to only have the first quadrant in my graph. So let me make this a little bit bigger so we can see it. Okay. Now once again, x is going to represent my minutes. And up here my C of x is going to represent my dollars. And now I'm going to graph it. My minutes go from 0 to anything beyond 450. Normally we would go 1, 2, 3, but I don't think I want to make it single minutes because, oh my goodness, that'll make this graph a little bit too big. So maybe instead I'll go, well, maybe by, let's make each one of these 100. So this will be 100, and I've got 200, and 300, 400, 500, 600, and 700, and so forth. Now, my cost here is going to be, it starts at $60, so perhaps, and again, instead of making each one of these 1, maybe I can make each one of these 50. So here's $50, 100, 150, 200, 250, and so on. Now, in order to graph it, notice that my time, my x, going from 0 to 450 right here is a flat rate of $60. It doesn't fluctuate. It doesn't change at all. So if all the way up to here, right, this point right here, it's going to be 60 bucks flat rate. Now this would be 75, so a little bit below that. Gonna look like this. All the way up to 450. Now the 450 is included, so I'm going to put my closed circle there. Now, beyond 450, remember, I'm going to take on a new function, this one right here. The easiest way to do this, now notice, if I was to distribute that 0.35 through, take a look at what would happen. Distributing the 0.35 through, I would get 60 plus 0.35x minus, and then, let me see here, can't remember what 35 cents times 450 is. Okay, so 35 cents times 450 is 157.5. And then when I take that negative 157.5 and add it to that 60, or combine it with that 60, I'm going to get a negative 97.5. And what I really want to stress here, the reason I went through this is to point out this is a linear function here. First power x, that indicates this is going to be a straight line. So in other words, this portion of my function is going to be a straight line. Notice this looks like y equals mx plus b. My slope here is 0.35. Here is my y-intercept. So being that it's y equals mx plus b, my slope being 0.35, that's a positive number. And if you recall, positive slope is going to go like this, that puff puff positive where the skier went in this direction. So my slope, my line on this portion of the graph, this part of the function, it's going to look like this. So what I'm thinking is, okay, that 450 hit here, the rest of the graph is going to be out here somewhere, a line looking like this. So frankly, the easiest thing that I could do for myself, now I could go ahead and try to graph it this way and say, well, a negative 97.5 is the y-intercept down here, and then I would come up 35, right 100. But honestly, the easiest thing to do would simply be to say, let's pick an x value back here, plug it in here, combine the numbers, and figure out where that point is going to sit. Now, pick a number back here that's easy to work with. I'm looking at this and I'm saying, hey, what if I stretch this out a little bit further, and let's say I went 900 and then 1,000, because 1,000 is a nice, easy number to work with. So what if I chose to say, let's call my x 1,000, put 1,000 right in there. And then I would take 0.35 times 1,000 minus 97.5, or if you would prefer, I can take my 1,000 and put it right in here. Now here, I would do 1,000 minus 450, and 1,000 minus 450 is 550, and then I would take my 550 and multiply it to 0.35. Now 550 times 0.35 plus 60 is actually going to be 252.5. 252.5. So, in other words, if I made my x 1,000, this would become 350. 350 minus 97.5, again, is going to give me 252.50. And that would be the cost of my cellular plan if I talked for 1,000 minutes, because that 1,000 minutes would be 550 minutes beyond my 450 minute limit. So what I'm going to do is I'm going to say 1,000 minutes, I'm going to come up to 252.5. Here's 250, so 252 is just going to be a hair above it. And so that's going to sit right about here. And so that means this portion of the graph is going to connect like this. And ta-da, there it is. So in this situation, notice what's happening here is that I am, let me get this out, there we go. And this is going to be for x greater than 450. Golly, all my greater than symbols look like sevens. There we go. And notice what I did here is I put an arrow on this, and why did I put an arrow on that? Absolutely, because it's technically going to go on forever in that way. Now, I'm not going to talk for a forever number of minutes. I'm not going to let my cost go on forever either. But technically, it should go on forever. Now, notice I did not put an arrow on this one because, no, I'm not going to go into negative minutes. I'm not going to go into, well, negative cost definitely, but I'm not going to go into negative minutes here. So this is what my piecewise function will look like in terms of its graph. Here's the function itself, including this, and here is the graph. Now, what if I needed to evaluate it? For instance, what if I was asked, okay, evaluate this for minutes being, in other words, let's say I want to evaluate it for that x being 1,000. Then what you would do if you were told evaluate it for x of 1,000, that would be my cost function at 1,000. That's what it would look like. And so if I was asked evaluate the cost function of 1,000, I would have to discern which of these two I'm going to use. 1,000 being the x means not in this part down here. And so I would take this function, put 1,000 right in there, and do what I did just now. Take 1,000 minus 450 is 550. 550 times 0.35 is again going to be, I still can't remember what that is, 192.5, and 192.5 plus 60 will give me that 252.5. What if I was asked to evaluate cost function of 100? So my x, instead of being 1,000, being 100. Well, what that would indicate is, take this cost function and find, okay, when x is 100, does that meet this one? No, that's only for x's that are greater than 450. That fits this one, where the x is between 0 and 450. But in this function, my cost is simply $60. So in that case, my cost function would just be $60 flat rate. So yes, you can look at this graph saying, okay, if my x is 100, that's right here, cost function 60. If my x is 1,000, that's going to sit here, and I have to kind of estimate how much that is. But frankly, it's much easier if you're told to evaluate your cost function at a particular x, use the function itself. So with that in mind, let's take a look at a few more examples. Like I said, I like this one just because it gives you a sense of, oh yeah, this stuff really does apply in the real world. Now, notice in these three examples, I've got these different functions. It's not necessarily a cost function, it's just a generic function. I'm told I want to graph each one of them. I want to state the domain and the range, which I didn't talk about in the previous one. So when I get done with this, let's go back and look at domain and range on that one. But here, in order to graph it, notice this says, if my x is less than 0, not including 0, just simply less than 0, then my function is going to be this right here, negative x. So I'm going to say, okay, x being 0 is everything, or less than 0 is everything on this side of my graph. Here's all my negative x's. So I'm going to graph a negative x. Now what that indicates is this is going to be a line, and it's going to have a y-intercept at 0. And then what I'm going to do is I have a negative 1 slope. So from here, what I'm going to do is I'm going to go up 1, left 1, up 1, left 1, or for that matter, I'll go down 1, right 1. And so my line's going to go like this. Now, it should go all the way through, but remember, this is only for x's that are negative. So my line actually is going to go like this, and it's not going to do anything up here. Now, for the second half of the graph, for everything up in this portion, and technically I would have an open circle right here for that portion of the graph. However, it does pick up and says, okay, when x is 0, or anything above 0, that's going to be the positive end over here, then my graph would be this function right here, just simply an x. So that would be kind of like saying y equals x. If that's the case, then what that tells me is I'm going to have a y-intercept of 0, and then my slope is going to be a positive 1. Positive 1 being, okay, I'm going to go up 1, right 1, up 1, right 1, and continue that on. So my graph will look like this and be on this side. Now technically my graph would extend on down like this, but remember, that's only for this portion right here where all the x's are positive. So I'm going to ignore this part for this graph, and it's not going to have that portion right here. And that's what my graph will look like. So now, in order to determine that domain and that range, this is old stuff here. Domain, remember, is all the x's. So if I take this graph and I squish it up on that x-axis, that's everything from negative infinity to positive infinity, because it's all the x's. So my domain then is negative infinity to positive infinity, just like we've talked many times. And infinity always gets a parentheses. Now that range, remember, range is all the y values. So I'm going to take this graph, I'm going to squish it up on this y-axis. When I squeeze it up on the y-axis, all this comes over here, this comes over here. Everything from 0 up got covered. So from 0 to positive infinity gets covered. And like we said before, infinity always gets a parentheses. Now, is that 0 a part of the graph? Most definitely. Not a part of this graph, but a part of this graph. So it does get included, and it gets a bracket. And there's your domain and your range. Okay, let's take a look at the next example. Similar idea here. I've got my function in two parts. For the top part, that's for all the x's that are less than a negative 2. Well, here's x negative 2, so I'm talking about all the x's that are on this portion. So what I'm going to do is I'm going to say on that portion, this would be my graph. That is the equivalent of y equals x plus 3. To graph that, I'm going to use, it's in slope-intercept form, so I'm going to say my y-intercept is 3 right here, and my slope of positive 1 means go up 1, right 1, up 1, right 1, or for that matter, go down 1, left 1, down 1, left 1. And so this is what my graph is going to look like. And it would cross right down here at -3. So my graph should connect like this. Notice that's for all the x's that are less than -2. So right here at -2 would be the beginning part, and it would go down like this. Pretend it's a straight line. I cannot draw a straight line to save my life. So that's what my graph would look like. Now I have to decide, does this get an open circle or a closed circle? Open circle, because that -2 is not included. Open circle right here. Now I know in the past I didn't worry about it, but that's because it picked up, it connected very well. Technically I should have said, well, I'm not sure, I'm going to put an open circle there, but then when it connected beautifully and touched, I should have closed that circle in. Watch what happens here, because this is going to be different. This one is for all those x's that are greater than that -2 or equal to that -2. So you would think I'm going to close that in with a closed circle and just keep on going. However, this graph is for y equals x minus 3. So when I graph that one, again, it's in slope-intercept form, so I'm ready to go. My y-intercept is -3 right down here, and my slope of +1 means go up 1, right 1, up 1, right 1, up 1, right 1. It'll cross right in there. So it's going to go like this, and then down 1, left 1, down 1, left 1, going to go like that. This is for all those x's that are -2 or bigger. Well, here's that x of -2, so it would pick up here, and it would go up like this. Notice they don't touch. So here where they did touch, I said it kind of doesn't matter whether it's closed or open, it's going to be closed because they touch, and that 0 is going to get accounted for, but here they don't touch. So it's very important that this one gets that open circle, because on this portion of the graph, that -2 point, where the x value is -2, that point right there is not included in this graph. It's included in this graph, so it gets a closed circle down there. And that's what your graph will look like for that particular piecewise function. And you can see, yes, it is in pieces. Not only is the function itself in pieces, but the graph is in pieces, as was the case here. A piece over here and a piece over here. And frankly, that was the case in the first one we looked at. We had a flat line there, that was a piece, and then we went boom, like that. That was your second piece. So now again, let's talk about that domain and that range. Domain again is those x's. So if I take this and I squish it up on that x-axis, now remember, all that's going on forever, so all these x's to -infinity will get covered. This is going on forever, so all the x's to +infinity will get covered. The question is, and everything in between, but what's going to happen right here? That -2, will it get covered? Well, as I squish it up, remember, this point's going to come up here. Aha, the -2 will get covered. So from -infinity to +infinity, there's no gaps at all when I squish this up on that x-axis. So my domain is, in fact, -infinity to +infinity because there was no gap. Now let's take a look at that range. Again, range being all those y-coordinates. So as I squish this graph up on this y-axis like this, it's all coming together, and notice that it's going forever up, it's going forever down, and this hole got covered right in there. So there is no gap at all. There's nothing that got skipped over. So that means that my range is as well from -infinity to +infinity. Okay, last one. Notice this one is in 3 parts. Piecewise, I mean, it's not restricted to 2 parts. It could be all kinds of parts. But the first portion says, okay, for all the x's that are less than a -4. Well, here's -4, so this is talking about all the x's back here. If these are the x's that we're talking about, it says that my function is just, frankly, a 0. And so therefore, it's a flat line 0. All the y values are 0. So for this particular function, from here back, all the y-coordinates are 0. That's going to look like this. Now, once again, this -4 should not be included, so I'm going to go ahead and put that open circle in there, and we'll see if we're going to fill it in here in a minute. That's the way I really should have done it up here. I just did not do the greatest job there. Now, from a -4 up to 0, not including the 0, but including the -4, this is what my graph would look like, that negative x graph. Recall, that looks like y equals -x. That is a y-intercept of 0 right here, and a slope of -1 means go up 1, left 1, up 1, left 1, or down 1, right 1, down 1, right 1. So the line's going to look like this. I just need to remember that as I'm trying to draw this line, it's going to go from a -4 to a 0. So the line, honestly, is not going to, it's just going to go, let's see here. Let's go up one, right one, oh, sorry, up one, left one again, and up one, left one more time, up to there. So it's going to look like this. And remember, that does include the -4, so there's going to be a closed circle here. Aha, this is an open circle because they don't actually touch. And then here, another open circle, and it's not going to extend down because remember, that stopped at 0. Did not include it, so it's open circle. And then let's see what happens for the rest of the graph. So the rest of the graph is for the x's that are greater than 0 or 0 itself. So here's 0 itself, here's greater, so it's everything back here. Now that graph is y equals x squared. So for y equals x squared, remember that's a parabola that looks like this. So my parabola will start here at 0, 0, and then it'll go up to 1, 1, 2, 4, up like this. It should go back here, but remember it's only for this portion of the graph, from here up. So therefore it's going to go like this. And I've got to figure out what to do about this 0 right here where they touch. It is included in this portion of the graph, so it is in fact going to be a closed circle on that one. And there's what my graph looks like for that particular piecewise. Crazy looking graph, absolutely. But this is what it looks like. So now I just need to determine my domain and my range. Domain again is all those x's. So as I squish this up on this x-axis, notice this will come down and cover that. And it goes on forever that way. This technically means it's going to go forever like this, forever this direction. So every single x is a part of that graph. Every single x it covers. Every single x is included. My domain is negative infinity to positive infinity. And again, infinity always gets a parentheses. Now let's talk about that range. Range again is all the y values. So as I squish this up on the y-axis, notice what happens. All of this will come back through here. All this goes over here, all this goes over here, and it's going to go forever that direction. So we'll go forever to infinity. But what about down here? No, there's nothing. So it begins at 0, but it does go all the way to infinity, which gets a parentheses. Now, that 0, is it a part of the graph? Is it included? Absolutely. So it gets a bracket, and there's my range. Now, let's go back and talk domain and range on this one, and then I want to take a look at evaluating, kind of like we did right here when we said how would we evaluate cost of 100 or cost of 1,000. Let's talk domain and range on this one. Domain again is going to be your x values, and notice on this particular one, as I squish this up on that x-axis, all this is coming down here, all this is coming down here. It's going on forever in this direction. So it is going to go on to positive infinity, but does it go to negative infinity? Absolutely not. It starts here at 0. So it starts at 0, goes on to infinity, which gets a parentheses. Now, is that 0 a part of the graph? Yeah, I mean, technically we could talk for no minutes at all. So that is going to get a bracket there, and that's going to be my domain. Now let's talk range. Range, again, is the y values. So let's squish this graph over here on this y-axis, squeeze it all like this. All of this will come over here, and then all this will come over, and again, it's forever in that direction. So my y values, as we look at all that gets covered, it starts right down here at 60, but it does go on forever and infinitely up, which gets a parentheses. Is that 60 a part of the graph? Certainly. So it gets a bracket. Now, one last thing I want to do is I want to go back to these, and I want to look at that idea of evaluating. So say, for instance, in this particular graph, and I think this one will suffice, what if it said I want to evaluate for instance, f of negative 10? Well, what I have to do is I have to go through all of these, because f of negative 10 means I'm making my x negative 10. So I need to go through these and say, which of these does x of negative 10 fit? It fits this one. So therefore, that means it'll be this portion of the function. Therefore, f of negative 10 is simply going to be a 0. What if I needed to evaluate, say, for instance, f of negative 1? Well, f of negative 1 does not fit here because this would indicate x being a negative 1. Negative 1 is too big for this. Negative 1 fits in this range right here, in this interval. So f of negative 1 means I'm going to work with this function. That means I'm going to take a -1 and put it right here for this x, which would indicate the opposite of -1. The opposite of -1 is a +1. So therefore, my evaluation of f of -1 would be a 1. What if I was told to evaluate f of 3? Well, 3 doesn't fit here, it's too big. 3 doesn't fit in this interval. 3 fits this one because it's greater than 0. So that means I'm going to make my x3 and put it right in there. And then I'll do 3 squared, which 3 squared is 9. So my f of 3 will simply be 9. What if I was asked to evaluate f of 0? That's tricky because I see zeros in both of these. This is where the idea of the equal to part is very important, because f of 0 would indicate, nope, not there, because it's not included in that one. 0 is included in this one. So to evaluate f of 0 means take this function, now put a 0 where that x is. And when I put a 0 where that x is and I square it, I just simply get a 0, so f of 0 would just be 0. And that's how you evaluate. Let's go ahead and take a look at this one just for good measure. In this one, let's say that I was told to evaluate f of -3. F of -3 would fall in this one because it's smaller than -2. That would indicate take this function, put a -3 right where that x is. So that would be a -3 plus 3, which is 0. So f of -3 would be 0. What if I was asked to evaluate f of +3? Well, +3 falls within this one. So that means I'm going to use this function and put a 3 where I see the x. So it'll be 3 minus 3, which is 0. So f of 3 would be 0. And what about, here's the tricky one, what if I was asked to evaluate f of -2? Again, -2 is that breaking point for my intervals. -2 is not included in this one, it's included in this one. So if I need to evaluate f of -2, I look at this part of the function. So I'll put a -2 right here where I see the x, and that will give me -2 minus 3, which is -5. And so my f of -2 will be -5. So hopefully that helps you with piecewise functions. First off, how to write them, which we looked at in the first example. Second off, how to graph them. Then how to figure out the domain and the range. And then being able to simply figure out how to evaluate that piecewise. Now please understand that if you are asked to evaluate a piecewise, you can see that when I did it for this case and this case, I didn't even look at the graph. So you don't have to have a graph in order to evaluate your piecewise function. You just need to have the pieces of the function and then determine, well, based on what this x is, which part of that function am I going to use in order to evaluate it. So I hope that helps. Have an awesome day.